Under Viksit Bharat Buildathon, we some students of PM Shri Kendra Vidyalaya Bakshi Ka Talab have brought up with an idea of thermonuclear reactor to generate electricity and counter the energy crisis in India. A thermonuclear reactor is a device designed to generate electricity by harnessing the energy released from nuclear fusion. The process of fusing light atomic nuclei like hydrogen isotope into heavier ones like helium, similar to what happens in the sun. Creating a thermonuclear reactor to generate electricity is driven by urgent global needs and long-term energy goals. It can offer a clean, safe, and powerful solution to meet the world's growing energy demands while protecting the environment. India's energy demand is rising due to population growth, urbanization, and economic expansion. When supply, especially coal and renewables, fails to meet peak demand like during summer months, power shortages are reported. Outputs of such a reactor are thermal energy, heat. The primary output of fusion is heat generated when light atomic nuclei like deuterium and tritium fuse into heavier nuclei like helium. This heat is used to convert water into steam, which then drives turbine to produce electricity. Second output is electricity. The ultimate goal is to produce electrical energy for homes, industries, and infrastructure. Energy is generated via steam turbine connected to electrical generator, similar to conventional power plants. Third output is helium gas. Fusion of hydrogen isotope produces helium, a harmless and non-radioactive gas. This can be collected and used in industries, example cooling system, welding, medical imaging. Fourth output is neutrons. Fusion reactions release high energy neutrons which transfer energy to surrounding material like the reactor blanket, can be used to breed tritium from lithium for future fuel, may also be harnessed for material testing and scientific research. Fifth output is minimal radioactive waste. Unlike fission reactors, fusion produces very little long-lived radioactive waste. Some reactor components may be mildly radioactive but not that much, it is manageable. A thermonuclear reactor significantly more energy per unit of fuel than a uranium fission reactor with far less radioactive waste and greater fuel abundance. Materials and required capital. Key materials required: fusion fuel, that is deuterium from water, tritium, that is breeded from lithium or produced in reactors. Structural material: stainless steel, tungsten, and beryllium for high temperature and radiation resistant components. Superconducting magnets: niobium tin, that is Nb3Sn, and niobium titanium, that is Nbti, for magnetic confinement systems. Blanket material: lithium containing ceramics or alloys to breed tritium and absorb nutrient energy. Plasma facing component: carbon composites and tungsten to withstand extreme heat and particle bombardment. Coolants and insulator: helium water or liquid metal for cooling. Ceramic insulator for electrical systems. The estimated capital investment. Total cost range between 14 billion US dollar and 30 billion US dollar for a full scale reactor like ITER. Breakdown: direct cost, reactor core, magnet, turbine, and cooling systems. Indirect cost: land, licensing, engineering, safety system, labor. Time factor: delays and technological challenges can double the cost over time. Invention design process. Conceptual design. Choose a fusion method, typically magnetic confinement using a tokamak or stellarator. Define goals: electricity output, fuel type, deuterium and tritium, safety systems, and scalability. Second, site selection and infrastructure. Select a geologically stable location with access of water and grid connectivity. Build facilities for the reactor control system, cooling tower, and power distribution. Core reactor construction. Plasma chamber, A vacuum vessel where fusion occurs. Superconducting magnets create strong magnetic field to confine plasma. Blanket system surrounds the chamber to absorb neutron energy and breed tritium. Cooling system transfer heat to water to produce steam. Fuel preparation extract deuterium from water, produce or breed tritium from lithium blankets inside the reactor. Energy conversion use heat for fusion to generate steam. Steam drives turbine which rotates generator to produce electricity. Control and safety system install sensor, AI-based control and emergency shutdown mechanisms. Ensure radiation shielding and contaminant protocols. Testing and commissioning run simultaneous and low power tests, gradually increase plasma temperature and fusion rate, monitor energy output and system stability. The eighth is grid integration. Connect the plant to the national grid, use transformers and substation to distribute electricity. Let's conclude. A thermonuclear power plant that generates electricity through nuclear fusion stands as a beacon hope for sustainable energy future. By replicating the sun's power on Earth, it offers a clean, safe, and virtually limitless energy source. Like unlike fossil fuels and conventional nuclear fission, fusion produces no greenhouse gas and minimal radioactive waste, making it ideal solution to meet the world's growing energy demand while protecting the environment. Thank you.